Okay, so question 2, we have this reaction taking place, and it tells us that at the beginning all we have is some carbon dioxide, and that we add some solid carbon to it, and that's what triggers the reaction. So at the beginning the gas phase only contains carbon dioxide, and as the reaction proceeds we can see from the graph this is the concentration of carbon dioxide. Make sure you get that the right way around, so again maybe worth scribbling that on the graph so that you make sure you remember which one you're talking about. So that's the concentration of CO2, and it starts at 0.02 moles per dm cubed, and when it levels off that's when you've reached equilibrium. Okay, so this is the equilibrium carbon dioxide concentration when it stopped changing, and you can just read off what that is, and you can see that that's 0.004 moles per dm cubed. So what it asks us to do first is to see if we can sketch on the graph what happens to the concentration of carbon monoxide during the reaction. Well, we know at the beginning there wasn't any, because it told us that in the mixture, that all we had at the beginning was CO2. So our line is going to start at 0. Okay, so we know it's going to start there because it tells us that there wasn't any CO at the beginning. And then we just do the same kind of calculation that we did with the table in question 1 and look at the overall change in CO2, and you can see the concentration of CO2 dropped from 0.02 to 0.004. So we can write down the change in the CO2 concentration is equal to 0.020 minus 0.004, which is 0.016 moles per dm cubed. And the equation tells us what that's going to do to the concentration of CO. The concentrations are proportional to the amounts, so we could have done this in moles, but it's easy just to stick with the concentrations and say, right, if this went down by 0.016, this one will have gone up, but by twice as much. Okay, so it's the same kind of reasoning. You've got to look at the numbers in the equation, say however much of this reacted, which is 0.016 moles per dm cubed, this will have been formed, but in twice the quantity. So that means that the change in CO concentration will be 2 times 0.016, which is 0.032 moles per dm cubed. So that tells us what the final concentration of CO will be, because we know it started at 0, so if it rises by 0.032, its final value will be 0.032. So you can just draw a line across here at 0.032 and say, right, that's where it's going to end up at equilibrium. And of course the point is that that's only going to level off when the concentration of CO2 levels off, because all the time the CO2 is decreasing, the CO will be increasing. So this levels off somewhere around here. So we draw the same kind of curve. So we want it to level off somewhere around there, and we just draw a curve. So it starts at 0, rises up, and then levels off. And you get something like that. So the key features you had to get right were it must start at 0, it must finish up at 0.032, and it must level off at about the same place. So that you can see that the forward reaction can't stop until the backward reaction has stopped, or vice versa. Now part B, it's asking us to write down the Kc expression this time for the reaction, and also to find its value. So this time we have a heterogeneous equilibrium because the carbon is a solid, and remember that if you have a solid or if you have a pure liquid as opposed to a solution, you leave that substance out of your Kc expression because it's effectively got a fixed concentration, so there's no point having it as a variable. So that just means that Kc will be the stuff on the right is the concentration of carbon monoxide squared, because there are 2 of them, divided by the only one on the left that's a variable is the carbon dioxide concentration. So that's the Kc expression. Turning now then to the value, all we've got to do is to get the concentrations and put them into that expression, and that's going to be easy because we've just got to read them off the graph. So the carbon monoxide concentration is the concentration when it's levelled off, because that's when you've reached equilibrium, and we know that's 0.032. So we've got 0.032 squared on the top line, and the carbon dioxide concentration at equilibrium, well, that's the CO2. Again, when it's levelled off, that's the concentration at equilibrium, and that was 0.004. So that's your calculation that you're going to do, and that works out to be 0.256. And the units, remember, you do learn the recipe for units of Kc. So again, as before, you take powers on the top minus the powers on the bottom, so 2 minus 1 is 1 in this case, and the units, remember, is moles to the x, dm to the minus 3x is the general rule. So when x is 1, that just gives you moles per dm cubed is the unit, and that's your answer. Now part C is now bringing in this idea that there's a connection between rates of reaction and equilibrium. So this was a little bit harder because you had to do some thinking here. But actually the first bit's straightforward, because all it asked you to do was to measure the initial rate of loss of CO2. So that's the curve that they had already given you, and what you were meant to remember from when we did rates of reaction is that if you want to get the rate at any point in time, you need to find the gradient of that graph. So the initial rate is going to be the gradient of that graph at the very beginning. So that means you've got to draw a tangent. So you get your ruler and you just make the best attempt you can to draw a line that just mirrors the slope of the curve right at the very beginning, like that. So you draw the tangent, okay, so that's your initial tangent, and you just have to find its gradient. So the gradient, remember, is the vertical change divided by the horizontal change. Different people are going to get different numbers. It's quite difficult to draw those. They're going to give you a big margin for error. They're more interested in seeing that you know in principle how to do it than in how good you actually are at drawing tangents. So you get the initial rate is equal to the gradient of the initial tangent So the vertical change, well, that's just 0.02 if you've drawn this. I mean, this is the obvious way to draw it. Just draw it all the way down to the 0 line. So the vertical change is 0.02. And the horizontal change, well, it depends on the line you drew. I got 0.4 as the intercept there. So it's 0.02 divided by 0.40, which is 0.050 is the number. And you have to think about units. Now, all these questions, it didn't prompt you for units. Actually, it did for this first one. But whether they do or not, you have to remember that every time you calculate something, you have to stop and think about what the unit should be. So rate, remember, it's just, you can work it out from the graph, from the way you work this out, because it was the change in concentration, which is moles per dm cubed, divided by time. So it's moles per dm cubed per minute is the number. So moles per dm cubed per minute is the unit of the rate there. So then in the second bit, it says, well, what's the rate constant for the reaction? And it's given you the rate equation. Okay, it's told you that rate is equal to K times the concentration of CO2 for the forward reaction. So we know the rate, we know what the concentration of CO2 was at the beginning, because that's that point there is 0.02, so we know those two numbers, so that's actually easy, and we just get K is equal to the rate divided by the CO2 concentration. Okay, that's simply sliding that diagonally over from the right hand side to the left, and that's the number we've just calculated there. 0.050 is the top line, divided by the initial concentration, which is 0.020, which, using my numbers, comes out to be 2.50. And again, you have to think about what the units should be. So units for K, remember, you work out the overall order of reaction, which in this case is just first order, because that's the only term in it, and the units are moles to the 1 minus x, dm to the 3x minus 3, usually seconds to the minus 1, but we're working in minutes. So again, you've got to be careful, it's going to be minutes to the minus 1, where x is the overall order, which in this case is 1. So moles to the 0 means that term is just times 1, so it disappears. Again, 3 minus 3 is 0, so that term also disappears, and it's just left with minutes to the minus 1 is the unit for a first order reaction. Right, third part, it now asks us what would the rate of the forward reaction be after 3 minutes, and this is where you've got to be really careful. The answer to that is not 0. You might look at this and say, right, 3 minutes is down here somewhere, and say, well, the concentration's not changing after that point, so the rate is 0. But remember that by this point you've got both the forward and the back reactions taking place, and the overall rate of change is 0 because the forward and the back rates are both non-zero, but they're exactly balanced. They're cancelling each other out. So that if it just asks you for the forward rate, it's not 0. What you have to do is just simply use the rate equation, okay? Because this rate equation says that whatever the CO2 concentration is, if we multiply it by K, whose value we now know, we get the rate. So actually, as long as you realise that, it's a very easy question, because at 3 minutes, the concentration of CO2 is that limiting concentration of 0.004 moles per dm cubed. Okay, so we can just say that the rate after 3 minutes will be equal to 2.50 times 0.004, which is 0.010. And again, it's a rate, so the units are moles per dm cubed per unit time, which in our case is per minute. Okay, so once you realise what you had to do, that was very straightforward. It was just simply plugging numbers into the rate equation. And you just had to be clear that that doesn't mean that the concentration is changing, because that's exactly balanced by the backward rate. And that's the point of part 4, which says, well, what is the backward rate? And so the answer is, well, it's the same. Okay, so that we've just calculated is the forward rate. And so the answer to part 4 is that the backward rate is the same. Okay, is also 0.010 moles per dm cubed per minute. Because if those two rates are exactly balanced, that's what dynamic equilibrium is all about. So if those two rates are the same, that's why the concentration doesn't change, which is what you observe.